We will now be learning how to calculate the concentrations of reactant and products when equilibria are attained in chemical reactions. We will first look at a problem for an imaginary reaction in which A is reacting with B to give you product C, and at a certain temperature, this reaction has an equilibrium constant of 6.4. So it states in this problem here that if in the equilibrium mixture, the concentration of A is 1.6 mole per liter and that of B is 4.0 mole per liter, we are required to calculate the concentration of product C at equilibrium, if that is the equilibrium constant at a certain temperature. So we're given three things. We're given the concentrations of A and B, and we are given the equilibrium constant for the reaction. So the first thing we do is to set up the expression for the equilibrium constant, which is equal to the concentration of C raised to the exponent 2 divided by the concentration of A raised to the exponent 2 times the concentration of B. Next, we substitute the values for A and C into the equation. So you know that is going to be, what is it for A, and that is what for B, and all of this here is equal to 6.40. So to solve for C, we make C squared the subject of the equation. If we make C squared the subject of the equation, then we have to take across all of these terms there. So it'll be equal to 6.4 times 1.6 raised to the exponent 2 times 4.0. And that turns out to be 65.5. And to find what C is, we take the root of that, and it turns out to be 8.1 mole per liter. So this will be the final concentration of what C is. We knew what the initial concentrations of A and B were, and now the concentration of C at equilibrium will be equal to that. In sample problem 2, we were told that when sulfur trioxide is heated, it decomposes to form sulfur dioxide and oxygen according to this chemical equation. Here we are seeing 2 moles per liter of that is decomposing to give you a corresponding number of moles per liter of sulfur dioxide and 1 mole per liter of oxygen. So we're told that we are having 4 moles of sulfur trioxide in a 2-liter flask, which when heated at a certain temperature shows that the equilibrium concentration of oxygen is 0.50 mole per liter. We now asked to calculate the equilibrium concentrations of oxygen, sulfur dioxide, sulfur trioxide, the equilibrium constant K, and the percentage reaction for the reaction above. So we're given the volume and number of moles of sulfur trioxide. So the first thing we have to do in solving such type of problem is to find the initial concentration of the sulfur trioxide by using this formula here. And this concentration will be equal to 4 moles divided by 2 liters. And this is what its initial concentration will be. So we know the initial concentration of sulfur trioxide, and we know that for oxygen. We are now asked to calculate the equilibrium concentration for sulfur dioxide. Again, we set up what is called the ICE table and show how sulfur trioxide decomposes according to these stoichiometric ratios. 2 moles are decomposing to give you 1 mole here and 2 moles here. Now that we know we are starting with only reactants, definitely it will break up or react to give you products. So we'll be decreasing the concentration of sulfur trioxide and increasing the concentration of oxygen and sulfur dioxide. And we'll be doing that according to the stoichiometric coefficients. We do not know how much is being decompose. So we'll let that be 2x. So we're taking away 2x from that side. This is going to be 1x, and that is going to be 2x because, of course, of their stoichiometric coefficients. We are given that the equilibrium concentration of oxygen is equal to 0.5 mole per liter. As such, we can know what that is, and we can know what this is, since we know what x is. Since x is equal to 0.5 mole per liter, this will be 1 mole per liter, and we're removing 1 mole per liter from that. So sulfur dioxide will be equal to twice what oxygen is. This is oxygen, and it ends up to be that. The amount of sulfur trioxide that we are decomposing will be equal to 2 minus 2x, and we know that 2x is equal to that, and this is what will remain for sulfur trioxide. So you look at the equilibrium concentrations, we'll have that concentration of sulfur trioxide remaining, that for oxygen, and that for sulfur dioxide. You want to know what is the equilibrium constant, we establish the expression for that, and we insert the values for oxygen, sulfur dioxide, and sulfur trioxide that are found at equilibrium. That is for oxygen, that is for sulfur dioxide, and this here is for sulfur trioxide. Doing the math shows that it is equal to 0.5. So the equilibrium constant is equal to 0.5. We must define the percentage reaction. If you look at the reaction, we can see that it has this stoichiometric coefficient for sulfur trioxide, that for oxygen, and that for sulfur dioxide. Had this reaction gone to completion, every 2 moles of this should have produced 1 mole of that and 2 moles of sulfur dioxide. So if we use the concentration of oxygen produced to find a percentage reaction, this is how you go about doing it. You can see that from 2 moles per liter of sulfur trioxide decomposing, we expected 1 mole per liter of oxygen to be produced. But we did not get 1 mole per liter. Instead, we only got 0.5 mole per liter. So we expected this, but that is what we got in reality. So this is how we calculate percentage reaction. It is equal to the actual yield divided by the expected yield. In this case, 0.50 mole per liter is the actual yield, but that was expected. We multiply that by 100% and we get 50%. So the percentage reaction is 50%. In an effort to determine what would happen if only reactants are placed in a container, if only products are placed in a container, and a mixture of reactants are placed in a container, we have these 3 scenarios. So in this container here, we are having only reactants, which are hydrogen and iodine. In this one, we are having only products, which in this case is only hydrogen iodine molecules. And in this container here, we're having a mixture of products and reactants. What scientists found is this, that in all 3 of these scenarios, reaction took place that resulted in equilibria having mixtures of both reactants and products. The first container ended up with both reactants and products. In this one here, we start with only products. It is found that the products reacted to form some amount of reactants, iodine and hydrogen. And in this one here, there was a different composition of reactants and products when compared to that. This is how hydrogen and iodine react to give you hydrogen iodide. What scientists found was this, that the concentration of the iodine times the concentration of the hydrogen divided by the concentration of hydrogen iodide raised to the exponent 2, in every case give the same value. These here are some summary statements that relate to the illustrations above. Container A had only reactants and ended up with a mixture of products and unreacted reactants. So we're saying that an equilibrium can be attained by starting with only reactants. Container C had only products and ended up with a mixture of products and reactants at equilibrium. So the next point that can be made is that equilibrium can be attained by starting with only products. Container B had a mixture of products and reactants and ended up with different composition of these at equilibrium. So we can say that an equilibrium can be attained by starting with a mixture of reactants and products. Those findings can enable us to know in which direction a reaction will proceed, particularly so if you're starting with only products or reactants. So let us suppose that we had hydrogen iodide as reactants. We know that for sure it will break up to produce iodine and hydrogen according to its stoichiometric coefficients. We don't know how much is breaking apart, so let it be 2x. So you move 2x from that. We add 1x to this because this is a 1 here, not shown, and this is also a 1 here, okay? So we know for sure when you start with only reactants, the concentration of the reactants will decrease and the concentration of the products will increase according to the stoichiometric coefficients. On the other hand, let us suppose we are having another reaction in which only iodine and hydrogen are present. In this case, the concentrations of hydrogen and iodine will decrease, and that of hydrogen iodide will increase. So we are now removing from these and adding to hydrogen iodide. We now look at a problem in which we are starting with only reactants and we are asked to calculate the concentrations of all the species at equilibrium. So in this case, we are starting with that concentration of both, which are reacting to give carbon monoxide and water at 1,000 degrees Celsius, and the equilibrium constant for which is 1.2. Now that we know we are starting with only reactants, we can now set up our ICE table. So according to this ICE table, these are the initial concentrations of carbon dioxide and hydrogen, and we are having 0 concentrations of carbon monoxide and water. Definitely, because we are starting with reactants, the reaction will proceed to the right. As such, the concentrations of the reactants will decrease, and these here will increase, of course, according to the stoichiometric coefficients, which is 1, 1, 1, 1. So at equilibrium, we're going to have that for carbon dioxide, that for hydrogen, that for carbon monoxide, and that for water. Setting up our equilibrium constant expression, we get this, and that is equal to 1.2. We do not know what these are, so we put x to represent those, and these ones will be represented by 0.20 minus x squared, because we're having this twice, right? And that is equal to 1.2. To solve for x, because you're having a perfect square, if we take the root of that and the root of this, we'll end up with x divided by 0.2 minus x. So we take this term across there, we'll have x remaining here, and of course this is going to multiply everything there comes across. That's why you end up with that here. This is 1.1x. When you take this across, because of this negative sign, it becomes positive. So you're going to have 2.1x is equal to that. And x will be equal to 0.11 mole per liter. Now that we know the value for x, we can find the concentrations for all the species at equilibrium. We'll bring down this part of the table and insert the value for x and see what we have. So here we are subtracting x from that. We end up with this. Same thing here. and this is X here, and that is X here. So finally, we'll have all of these concentrations at equilibrium. For such type of problems, we're starting with only reactants. We know that the reaction will proceed to the right. Therefore, we'll reduce the concentrations of the reactants and increase those for the products. Or if we start with only products, we'll reduce the concentration of the products and increase those for the reactants. But for those problems that involve a mixture of both products and reactants, it becomes a little bit more challenging. And this brings us to what is called the reaction coefficient Q. Let's look at the typical problem and see how we utilize what is called the reaction coefficient Q to help us solve this problem. In a closed flask at 1000 degrees Celsius, we are having a mixture of carbon dioxide, hydrogen, carbon monoxide, and water. Now they're giving you that K for the reaction is 1.2 at this particular temperature here. And we are asked to calculate the concentrations of each of these at equilibrium. We do not know if the reaction is at equilibrium, nor do we know if it's going to go to the right or the left. So the first thing we do is to establish a K expression for that reaction. This reaction is the same one as above, where carbon dioxide is reacting with hydrogen to give you carbon monoxide and water. So these will be the products, and these, of course, will be the reactants. So that is our K expression. The next thing we'll do is to find what Q is. Q is really a value that is obtained by putting into this expression here all the values for the products and reactants that are provided in the question. So in the question there, we're given these concentrations of carbon monoxide, water, carbon dioxide, and hydrogen. And when we do the math, this is what we get. But that is not what K is. This is a value that we call Q. Now if we compare Q with K, we see that Q is less than K. So what is happening in these types of reactions is that there will be internal adjustments between the products and reactants in such a way that when the final equilibrium concentrations are attained and you put them in this expression here, you will end up with a value of 1.2. As these concentrations are, some types of internal adjustments have to be made between the product and reactants such that we end up with 1.2. We need to make this value here bigger. So to get this value bigger, we have to do two things. We have to remove from the denominator and increase the numerator. And the denominators in this case represent the reactants, and the numerators are the products. It means we have to remove from the reactants. It means that the concentrations of the reactants must decrease by a value X, and these will increase by the same value X. These will be the final concentrations of the reactants and products at equilibrium. We know that K is equal to that when these are the concentrations of the products and these are the concentrations of the reactants at equilibrium. Now you can see that this is identical to that. So you make it squared, and this one here, you raise it again to the exponent 2. Now you can see this is a perfect square. So if we take the root of these and the root of that, we got a value of 1.1. Now we have to solve for X, take all of that across, put those in brackets, and you multiply by this value here. So we end up with that is equal to that. This is equal to 1x here. When you bring across that negative, it becomes 2.1. Take that across, you subtract 0.20 from that, and you end up with this. So x is equal to that. Bring back our table there. and substitute the value for X in each case, you'll end up with these concentrations here at equilibrium. We have a similar type of problem that involves starting with both reactants and products. But in this case, now we're told that equilibrium constant for this reaction here is 1.5. Of course, it's the same reaction that we had in the previous example. All right? With carbon dioxide reaction with hydrogen to give you carbon monoxide and water. Same thing we'll do. We put all of these values into the K expression to get the value for Q. And Q turns out to be equal to 2.25, which is now greater than 1.5. So again, some internal adjustments have to be made such that the final concentrations of reactants and products, when placed into the K expression, must produce 1.5. How do we have the adjustment? You have to remove from the top and bring to the bottom. Now we know that these are products. The concentrations of the products must decrease, and the concentrations of the reactants must increase. So look what we're doing. You're removing from here, and add to these places here. Now when we put these into the K expression, it's like this. Again, it's going to be a perfect square because these two are identical. That's identical, that's identical. We raise that value to the exponent 2, that the exponent 2. Take the root of that, and we end up with that over that is equal to this. And math is easy now. Leave this by itself, take that across, multiply all of these here by 1.1. In the end, we end up with this expression here. Of course, this is 1x. When we cross the 1x, they become positive. We get 2.1x is equal to that, and x is equal to 0.4. Bring down that equilibrium part there of the IC table. Substitute for x. You end up here. So in the end, these here will be the new concentrations of your reactants, and this will be a new concentration of the products. Notice how the products have increased in concentration, and the reactants have decreased. This brings us to a different type of problem that involves the imperfect square. Now here you're having sulfur trioxide reacting to give you oxygen and sulfur dioxide, and K for that is 3.18 times 10 to the negative 11 at 35 degrees Celsius. You're asked to calculate all the species at equilibrium if you have that number of moles of sulfur trioxide in a 2-liter container at 35 degrees Celsius. So the first thing we do is to find the concentration of the sulfur trioxide. Using that formula, we end up with that to be the concentration of the sulfur trioxide. Establish your IC table. We know we're starting with only reactants, so we have to decrease the reactants and increase the products according to their stoichiometric coefficients. That is 2 minus 2 plus 2. This is 1 plus 1. So these will be the final concentrations at equilibrium, and our next job will be to find the value for x. Again, we set up our K expression, that times this to the exponent 2 divided by sulfur trioxide to the exponent 2. Insert these values here as the equilibrium concentrations and equate those with the equilibrium constant, which is this. When you do the math up here, it becomes 4x cubed. We'll try to simplify our calculations by seeing if we can remove this guy here. We're removing a certain amount of sulfur trioxide, right? We do not know if it is very significant to affect the original concentration that is present. So to know if removing this does not make a big difference, this is the rule. It's what is called the 100 rule. We take the initial concentration of the sulfur trioxide and divide it by the equilibrium constant for the reaction and see what it turns out to be. If this value here is greater than 100, then it gives us the leeway to remove this term from that expression. And we can see this is much higher than 100. So we now simplify our expression by removing this 2x. And this is what we remain with. So we say that that is approximately equal to that. So solving for x now, we have that 4x cubed is equal to that, x cubed is equal to that. Take the cube root of that, you end up with this. All right? You round it after this. So in the end, sulfur trioxide is going to be equal to that value there. Because you have to subtract 2x from that. And this is what the final concentration of your sulfur trioxide is going to be. Now, there's something else you have to talk about. There's something that's called the 5% validity rule. To know whether or not our assumption is valid, we're going to see if the difference is less than 5% of what the original concentration of the sulfur trioxide was. So the initial concentration of sulfur trioxide is this, and this is the approximated value. And the difference is that when you subtract this from that. To find the percentage difference, we take this value, put it over the initial concentration times 100%, and is equal to 0.11%. It's much less than 0.5% of what the original value was. So if it were greater than 5%, then the assumption would have been invalid and one will have to use the quadratic equation to solving the problem. So putting in all these values, we'll end up with these concentrations here. We'll now look at a problem that involves the use of the quadratic equation. So this is a problem. At this temperature, hydrogen iodide decomposes into hydrogen and iodine. Now you're told that that amount of hydrogen iodide is placed into a 2-liter flask at 406 degrees Celsius, and you're asked to calculate the concentration of all the species at equilibrium. So you're given the volume, and you give number of moles, and you're given the equilibrium constant. Solution. First thing you do is to find the concentration of the hydrogen iodide by using that formula there. And it turns out to be equal to 0.5 mole per liter. Now we know you're starting hydrogen iodide as the reactant. Definitely the reaction will go to the right. We remove concentration of the reactant and increase that for the product according to the stoichiometric coefficient. And we know what that is. So this will be the final concentrations of all the species at equilibrium. We establish our K expression. Insert from the table what we have. X, 0.500 minus 2x raised to a coefficient of 2. That's equal to 50. Is it okay to remove that term there from the original concentration without affecting it significantly? So apply the 100 rule. We take the initial concentration, divide by its equilibrium constant, and you can see, look, it's much less than 100. Only if it were greater than 100, then we could have removed that. So now we cannot apply that rule here. We have to continue solving the problem using the quadratic equation. So this square here will be equal to 50 times all that which we have taken across. When you do the math, you end up with that. If you take across the x squared, it becomes 199x squared minus that plus that. But now we can divide everything by 100. Dividing everything by 100, we end up with these final concentrations here. This will be A, that's going to be B, and that's C when we apply these to the quadratic equation. X will be equal to minus B plus and minus whatever the square root of B squared minus 4AC. All of that divided by 2A. Doing the math, we ended up with two values for X. Either this one here or that one there. Our next job is to substitute either of these one at a time into the equilibrium concentrations and see what it turns out to be. So using that, we'll end up with this value here for hydrogen iodide, that for hydrogen, and that for iodine. Putting these into the expression, we end up with 53. But K is equal to 50. So using this one now, and doing the math, we end up with this, and this. Putting these into the K expression, we ended up at 50.1. So apart from that little discrepancy there, we can now agree that that was the correct one to use. And these will be the final concentrations of all the species at equilibrium, the positive values. Thank you so much.